Our next talk will be by Anton Vikaeus. Would you like to share your screen, Anton?
Yep. So, right, I'm ready to begin, so I can start?
Yeah, go ahead.
All right, so hi, my name is Anton Vikaeus. I'm a PhD student working at Uppsala University. For the ones that don't recognize me or so on, I work with Erik Zachrisson and Martin Salén as supervisors. So I will continue now to present some work on a paper that's coming up quite soon when we're looking at the conditions detecting lens Popfree galaxies in blind surveys with JWST, RST, and Euclid, the ones that we applied it to. So is the paper with some collaborators. We also have Daniel Scherer, Eli Visbal, and a student, Emma Fransson, working with us, and Sanjita Malhotra, Jim Rhodes, Martin Salén. So thank you. I will pay tribute to those for their contribution. Right, so when we're looking for the first generation of stars or galaxies in the universe, so we wanted to be able to detect them. And to begin with, just some background here, if we're looking to detect Popfree stars, for example, as you all know, they form in mini halos at quite high redshifts, forming already at redshifts of 30 or so, that regime. So typically yields only quite low stellar masses. So if you're assuming a certain star formation efficiency here, fraction of baryons forming stars, you only have like 30 to 100 or so approximately worth of total Popfree stellar mass. So are they detectable? Well, that's quite unlikely. Even with very strong gravitational lensing due to their low brightness and their high redshift and their quite short signals, small systems. I should mention also, well, maybe there are circumstances where we can detect Popfree stars forming in some pockets of pristine gas that may remain pristine to lower redshifts. That's possible. These kind of cluster lenses, for example, that Brian just talked about in the previous presentation, we can get really large magnifications and maybe detect some of these really low metallicity stars or clusters of stars. So the Popfree galaxies that we've been considering or focusing on rather form in the atomic cooling halos, where you have atomic line emission cooling at redshifts of about 15 or so. The typical masses we're considering then are quite different. So they're at redshift 10, it may reach something like thousands or tens of thousands solar masses with a given star formation efficiency. So the kind of objects that we're looking for, I should also mention that we're put quite stringent requirements to these, because we're looking at pristine objects in the kind of the work that we're doing. So we're not looking at objects that had formed a significant amount of metals and which will pollute the signal and so on. But we rather try to stick to those ones that had really pristine signals. So that requires delayed star formation in the mini halos that makes up the structure for the bigger halo. So you have some mechanisms: Lyman-Werner radiation, dissociating H2, baryonic spinning motion, and ionized feedback, and that may suppress star formation, so that these atomic cooling halos may remain pristine to quite low redshifts, in which we hope we can detect a pristine signal. So are these detectable? Well, with gravitational lensing, they certainly are, as I will try to argue here in the coming slides. So the gravitational lensing that we apply adds a probabilistic aspect to the detection of these objects. So we apply gravitational lensing to randomly oriented sky surveys. So as opposed to targeting specific cluster lenses, for example, where you have very high magnifications, we did our calculations on random surveys rather, in which you can formulate a function here that tells you the magnification probability, or the probability of attaining a certain magnification, and that has the kind of scaling as you see here, as an inverse square, more or less in the relevant range where we're looking to detect Popfree galaxies. So when we're trying to detect an object, we want to have a certain magnification which will lift the object above the detection threshold of a particular telescope. So that's what we apply, and this places a minimum requirement on the comoving number density of these Popfree galaxies, and these are the ones that we calculate and then compare to simulations to see whether the amount of objects are enough, the comoving number density is enough to get a sufficient amount of them appearing in surveys in the future. So the kind of results that we got, I'll bring your attention first to the equation just to tell you so that you're understanding what figures comes from here. But what we do is we calculate the minimum comoving number density. This is produced from the magnification probability function, where you're looking at the magnification, which will bring it above the detection threshold of any given telescope. The comoving survey volume, so that depends on the survey area of the telescope, so how wide it will survey, of course. And it also has a dependency on the cosmic time span in that volume and how that relates to the lifetime of the signature if we're looking at truly pristine signal. So that goes into this as well. So the results here on the left, if we begin there, we have look for the helium ionized helium 1640 emission line coming from, that's argued a very specific line for us Popfree galaxies when we're looking to observe them. So what you can bring with you here from the figure is that this looks, you can see them as kind of exclusion plots. So the simulations which predict the number density of a certain Popfree galaxy of a certain mass ends up in the regime that you see here, more or less. We have the Inayoshi simulations down that's quite below here, and we can consider that as like lower estimates, but the ones on the top here maybe be reasonable estimates on the abundance of these objects. So they fall below the lines of the different telescopes here. So that means that we are define that as an undetectable regime. So unfortunately, spectroscopy on the helium emission line, ionized helium emission line, seems to be unprobable to detect these kind of objects in these surveys. We're applying our method to it. On the other hand, using photometry on the 1500 angstrom continuum in order to detect them, it seems this is another story, because in this scenario, several of the telescopes seems to predict that we would find them with photometry when we're applying our randomly oriented sky surveys here. So RST seems to be performing the best. Euclid also seems to perform quite well. So you can see here that the large survey area of telescopes like RST seems to be very fortunate very good for detecting them with photometry, while on the other hand, in spectroscopy, there seems to be a quite even game. But we also have restrictions on the maximum allowed magnification before we get differential lensing and these kind of problems that will compromise or make make it harder to understand what we're seeing, and we need to develop our models further for that kind of high magnifications. Yeah. So furthermore, looking at looking at a wider redshift range, we looked at these kind of model predictions here. We have different star formation efficiencies. So at the redshift 10, some of the predictions here, the Stiavelli case, the one that performs best here, comes really close at redshift 10, but that's only for a very high star formation efficiency, which might be quite unreasonably high. So we're rather considering realistic numbers to be around this line here, the red line, for example, here, or some of these lines up here above. So you can see that they're all over across this redshift range that we're looking at. It seems that we have some problems with the number densities falling quite short, and this is also for JWST with helium spectroscopy on the helium emission line here I mentioned previously. So the best area seems to be around redshift 10 or so, but also maybe at lower redshifts there could be also reason to believe that we could actually find them, but we haven't investigated the lower redshift range yet. So conclusions, we will likely detect, with our models, we predict that we will likely detect Popfree galaxies, pristine ones, photometrically, at least in the 1500 angstrom continuum. We will not be able to spectroscopically confirm that we have detected Popfree galaxies. It seems, with our models at least, that they're based on the ionized helium 1640 emission line being one of the good indicators for Popfree. It seems to say that the number densities are a bit too low to expect this. And some community homework I thought would be appropriate. So whether or not can maybe hydro simulations allow more massive Popfree galaxies to form, so higher star formation efficiency without sacrificing number density. So we have some requirements here. I won't go into that, but it seems if we can place the number densities at these kind of values, so a couple of thousand per cubic megaparsecs for a couple of thousand solar mass galaxies, that would do the trick. Yeah, so these are just some numbers here, and furthermore, like I just mentioned, the evolution of this at low redshift. So these kind of lines here would pan out at lower redshifts and level off at some point, and maybe simulations then at lower redshift could kind of converge on this, but we're not sure of that. Of course, when we're looking at that's increasingly being a lot of work done on that. So maybe that we'll find out more about that in the future here. So for that, I would like to just thank you for listening and going. Yeah.
All right, thank you, Anton. Give a minute for people to write any questions in the Slack. We'll just wait a few seconds for people to have time to write questions.
Yeah.
So what fraction of redshift 10 galaxies are population 3 dominated according to the simulation predictions you used?
What fraction in the simulation? So the prediction that we used and the Uppsala simulations, because he's one of the co-authors here, he's simulating them as pristine objects there. So I guess that would be all of them in that case, because that's been applied to just having no prior star formation, really. So that would be catching them quite early when they start to form stars. In the other simulations, we're just using the fact that they're predicting, for example, Stiavelli is predicting the number density of atomic cooling halos, and then we translate that into a mass. So in that case, it could be a wider range of whether or not there would be Popfree bright or not. It's fine. So
the next question is, why is the n-min value flat above a certain stellar mass range?
So I guess that would be the kind of figures that I took. I'm just taking them here. Yeah, these kind of flat areas here. So these are the areas where the telescopes do not need any gravitational lensing at all. So they're for the higher masses, you can see that the JWST is reaching quite deep here without the need for magnification. So when you're starting to bend upwards, that's when magnification kicks in. And the same thing here, you see also that they're positioned at different heights here, at different places on the y-axis, and that's the different survey area of the different telescopes. So I guess that was the question, I hope.
If any other questions pop up here.
Do your simulations show how the heavier elements are synthesized?
How the hell heavier elements? So not really. I wouldn't want to say too much about that. I haven't been involved that much in the simulation work. That's the work by, for example, Visbal, that's co-author. So I think that I would have to ask him more about how that works out and how you actually go over to the when you're saying that you're in a POP2 population, you're transitioning over. But that's definitely well defined when you're transitioning from pristine to metal enriched. Yeah, but what I could mention is that we're putting a certain lifetime on our object. So if you say that it begins to form stars, we won't wait longer than 10 million years before we're supposed to extract the spectrum. If we're looking at 10 million years after star formation is commenced, then we're considering the Popfree signature to be removed, and we would rather see an enriched galaxy.
All right, thank you, Anton. If anybody has any more questions, please put them in the Slack.